Hello everyone. If you're like me and follow what goes on in the machine learning community, or if you're new to machine learning and try to get a peek in, your impression would be something like this. We discuss a lot on deep learning, different algorithms, and you're made to believe knowing machine learning, doing machine learning is all about knowing the boosting algorithms and the RNNs. But in practice, my experience working on machine learning in real-world products, it looks more like this. It's about figuring out how to configure data pipelines, how do we manage the different models we have, and how do we monitor what goes on in the predictions? Is it doing fine? So in real world, it looks more like 10% of the time and 10% of the effort is on the algorithms, and 90% is on the systems that support your machine learning models. And that is the focus of my talk. What if we could turn this around and instead focus more on the algorithms, have systems in place that lets you focus more on the algorithms? I'm here to share how we did that, how we go about doing that at DoorDash. Through many iterations of applying machine learning in our products, we identified best practice solutions for a lot of the common problems that occur with using machine learning in production, build that into robust tools to form our ML systems. As I go through the talk, as I talk about the experience, I would talk about the implementation details, but I would focus more on the underlying concepts in the hopes that that's more useful to you in your own applications. Quick overview on the agenda. I'll start with what DoorDash is and where we use machine learning at DoorDash. Talk about how ML evolves in our product or in products in general, and then go deep on the different systems we have for machine learning, and end it with a couple of examples of how these systems have helped us ship more machine learning and ship it more confidently. To start, DoorDash. How many of you have heard of DoorDash? Quick show of hands. How many of you have used DoorDash? Looks like we're doing well. We also have good growth opportunity here. So DoorDash is a technology company that's focused on being the last mile logistics layer in every city. We do this by partnering with local businesses, by empowering local businesses to offer delivery. We connect them with consumers who are looking for delivery, and dashers who are the delivery personnel who are ready to fulfill the delivery. This gives rise to a three-sided marketplace: consumers, merchants, and dashers. We started about 5 years ago, focused primarily on restaurant delivery. For those of you here in New York, restaurant delivery, food delivery is something pretty common. That's not true across the US. It's a new and rapidly growing industry, and we aim to be in 1,600 cities by the end of this year. To give you a sense of the scale that we work with 100,000 plus restaurants on the platform and 300,000 plus dashers. And in the 5 years of experience, 5 years of operations, we have fulfilled tens of millions of deliveries. So let's start with the marketplace. I believe the best way to apply machine learning in any industry is to start with the customers, understand what they look for, and use machine learning as a problem-solving tool. So for us, there are three different customers. We have merchants, and the reason they use DoorDash is to increase their reach. And they want to increase their reach in order to make more revenue. For consumers, they use DoorDash so that they could focus on what they care about more. It's more about convenience. And what they look for in achieving this convenience is the selection that they could get, the ability to order from many different restaurants. For dashers, the main motivation is flexibility that DoorDash provides. They're independent contractors, which makes the work schedule really flexible. And what they want really is more earnings. So understanding these motivations for the different customers, and this leads to a lot of machine learning problems between the different customer segments. Between the merchants and the consumers, it's the traditional e-commerce application. How do we surface the best content we have, either on the app or on the website, through emails, through push? So that's a lot of recommendation and personalization algorithms. Between the merchants and the dashers, that's the core logistics engine. We have a bunch of dashers who are ready to fulfill the delivery. We have a bunch of deliveries on the platform. How do we make the best possible combination of this, the best possible assignment, so that we increase the efficiency of the marketplace and we fulfill deliveries as soon as possible? Between the dashers and the consumers, we have the big responsibility of making sure the marketplace is well balanced, which is we have the right supply, right number of dashers we need for the right demand we have, for the number of orders that they're coming through. This involves machine learning in the sense we have to predict the demand that we're going to have, we predict the supply we will have, and how do we balance these two? A lot of different pricing algorithms, other demand shaping and supply shaping strategies. In addition to the applications between the customers, we also have specific applications for each customer. For merchants, given the selection we have on DoorDash, we have all different types of food, starting from let's say the fast food places where the food could get prepared really quickly, or on the other hand, let's say deep dish pizza, which probably takes 20-25 minutes to prepare. There is a lot of variance involved in the merchant operations. How do we know there is a spike in the orders, spike in in-house orders at the merchant? Maybe it's weekend demand, maybe there's a dinner peak. How do we incorporate these into our machine learning algorithms to be able to predict food preparation time? For the consumers, you could think of traditional e-commerce applications again on predicting the lifetime value of the customer. How do we decide promotion structures for different consumers? For dashers, the most important machine learning application is the pay calculation. DoorDash uses an effort-based pay model, which means we look at the effort involved in fulfilling a delivery, looking into the complexity of the order, the distance you need to travel, the time it would take to process the order, and we try to make the pay consistent and fair for every delivery. So this is powered by a machine learning model. As I mentioned before, we do supply forecasting, and there is a lot of work on our own incentives for different dashers. Given we have a wide variety of applications, before building systems for these, it's good to understand what the requirements are. I like to look at this in this offline to online axis. On one hand, on the offline side, you have recommendation algorithms. Think of emails that you get from different people, different products. These don't have to be computed in real time. These are computed offline in a batch setting. On the other hand, we have, let's say, predicting the delivery times. As a consumer, if you order on DoorDash today, we'll tell you you'll get the food in 42 minutes, 36 minutes, whatever it is. This has to be real time. We don't know who's going to order. We don't know which restaurant they're going to pick. So once we get a delivery, we make the prediction. So that's more on the online side of things. And then if you take the example of demand forecasting, that's somewhere in the middle. We probably want to predict demand, let's say 2 weeks in advance to know what we are getting into. We also want to predict demand, let's say 20 minutes out, so that we can manage the marketplace in real time. For most of the talk, the systems I described cover both the offline and the online side of things. Just to keep it focused, I would run with an example of the online side. Particularly, I'll focus on the delivery time prediction. When you start with machine learning in a product, it doesn't start off with the super sophisticated models. Imagine it's the early days of the product and you are tasked with the project of predicting delivery times. How would you go about doing this? You'd start not with the state-of-the-art model, but with just simple rules. For this particular application, it could be something like this. Let's say in Manhattan, any delivery takes 40 minutes, or in Austin, it takes 35 minutes. This is a general idea. You could extend this out. You could say on Fridays the deliveries take certain time, on Mondays it takes certain other time. You also don't have a lot of data at this time, so this is sort of the only approach you could take. As you get more data, the next evolution is you run a regression, you identify the coefficients. You get some sort of an equation that says this is the ETA and this is how you would add certain factors to it. The way you would productionize such a system is you take these coefficients, these numbers, and pretty much just load it into your production system. That's the simple ML system possible there. As things evolve, you emerge onto more sophisticated models. For example, your first real ML model might be using a scikit-learn model that you can get off the shelf. You write your own feature extractors. Here is where you're actually getting into the real production ML side of things. And quickly enough, you see this is pretty powerful. You have many different ML models. One for, let's say, predicting the preparation time, one for predicting demand, predicting ETAs. And more often than not, each of these evolve independently. You end up with many different stacks for each model. Presumably different people wrote it. And at this stage, you're left with the decision of designing a true ML system. What do we need there? As your product grows, the performance of your ML system becomes really critical. When you start, you're probably not thinking too much about accuracy guarantees, but at scale, that becomes really crucial. For example, let's say the case of predicting ETAs. Let's say I tell you you're going to get your food in 80 minutes, and it's coming from a prediction. You're probably not going to order. You want your food as soon as possible. So that affects the revenue that the business makes. If on the other hand we tell you we'll get you the food in 20 minutes and then not deliver on it, that's not good either. And this becomes all the more important when your business is fulfilling lots of deliveries every day. So your ML system needs to provide certain accuracy SLAs. Similarly, system SLAs. When you're checking out your order cart, you probably don't want to be waiting too long to know when your food's going to be there. So there's requirements on latency, requirements on ability to scale as you grow. But the most important part of the requirement is the debuggability. Let's say you're running a model in production. there's going to be some case where it fails. And when it fails, you want to be able to identify what is going wrong. For example, let's say the prediction for ETAs is going up. Someone calls you up and says what's going on. You want to be able to quickly identify whether it's a data issue, it's a model issue, is the model stale, is it a dependency issue, you depend on someone that's not behaving correctly. And the ability to debug a system is how you can iterate faster on it. Innovation is usually powered through experimentation, and the crucial requirement to experiment is to be able to move fast, and which is where time to iterate on the models, time to ship the model becomes important. And as you build more ML models, you end up with a lot of dependencies. For example, the system to predict parking times would be a dependent of the system to predict ETAs. Or the system to predict real-time supply is going to impact the delivery times. So how do we manage these dependencies? How do we avoid writing a lot of custom code and actually leverage the economies of scale, which is you don't want to 2x the effort if you have 2x the number of models. You want the effort required to reduce. Given this, the way we approach this problem is we take the best practices, we templatize them, so we don't have to duplicate a lot of the effort. To attain the SLA requirements, to attain quicker iteration speeds, we build robust tools, and put these two things together, make your ML system. As you try to build this ML system, what principles did we follow? Templatizing the best practices. You don't have to work doubly hard for it. Ease of use. When the system is deployed, you want your data scientists and engineers to be able to use the system easily and effectively. You want the configurability to be easy, maybe put in as config files, not requiring a lot of code. The other requirement we set on ourselves is to bias towards simple tools. DoorDash is a fast-growing business. We don't want to over-engineer early, over-optimize early. Focus on building modularized tools, so each of these tools can evolve independently. And the last point is to integrate with the rest of the ecosystem. DoorDash is fast moving into a microservice architecture, and when we build these prediction and training systems, we want it to integrate well with the microservice architecture, reuse a lot of the monitoring and the logging systems that are in place. Just a quick intro on what goes on in machine learning. There's traditionally two different phases. There is training and prediction. Training is where you prepare your data, explore different model options, do model selection, run different algorithms. And then when you decide you have a good model, you take it into production. Once it's there in production, you want to monitor the system, and there is some maintenance involved. Going with the running example of predicting delivery times, training is done offline. You get your data from your databases, use many different scientific libraries, try different models possible, do it all offline. So the system we develop for that needs to be agnostic of the model choices made. It focuses on the iteration speed, so we can move quickly. The prediction part, though, that has to be real time, which means it integrates with the production systems, and scale becomes an important requirement. So let's talk of training first. This is a prototypical training pipeline. You start with the data, you have your features extractor, and then you have a training job, and you end up with the model that you put in the model repository. Let's go into each individual component here. Features extractor. The power of any supervised learning model comes from the features you use, the features you put into this. So for example, you're predicting delivery times. You design a lot of features. Let's say you look at historical delivery times in the particular market. You look at historical delivery times on the particular day, historical delivery times for this particular merchant. What's the subtotal of the order? How many items does this order contain? These are different features. So you design job, you write a job that looks at the data, calculates these features, cleans the features, standardizes them, and makes it ready for training. To make this more robust, we integrated this with the ETL pipeline. What is ETL pipeline there? We have many different jobs that run on a nightly basis that calculate different business metrics. For example, at the end of the day, we look at all deliveries that happened yesterday, calculate how long each delivery took to be delivered, how long the merchant took to prepare the food, how long the dasher traveled from one location to another. These are metrics that are calculated for business reporting purposes. What if we integrate the model training, the features generation part into the system, we could manage the dependencies more effectively, which is you can have the job that calculates the average historical delivery times for the merchant depend on the job that calculates delivery times for each delivery. So in order to do this, we use a job scheduler. In particular, we use an Airflow-based system. As we build a lot of these features, we identified a significant overlap between different jobs. The features job for delivery times and the features job for, let's say, the dasher time would require same set of features. For example, what's the parking time historically? So we found a lot of value in extracting these common features out into what we call a common feature store. These enable us to have standardized features. So not just the particular ML application could benefit from it, it could also be any future application could directly use the job. The best way to think of this is it's a key value store. Let's say there is a features table that contains all features of a store, of a merchant. The key could be what's the average delivery times in the last 1 week, and the value is whatever the average delivery time was. And exposing this for all different ML pipelines helps us standardize the practices, make sure the data is robust. Once you have the features, the next part is training the pipeline. We have a job that we use many different libraries like scikit-learn, lightgbm, keras. So in order to wrap all this and make it model agnostic, we use an ML wrapper. And again, to make use of the dependencies we already have in place, we integrate this into Airflow system. So the training job could depend on the features job, so it runs after the features job is ready. It also helps with scheduling, so you could schedule the training job to run, let's say, every day or every week, however the requirement is. Once it's trained, we add the data, we add the model file, which is a model object, into a repository. In particular, we use S3 as this data source for our models. In addition to the model object, we store metadata on, let's say, the training data used, the training time, parameters used. Moving on to the predictions part. The use case we have here is, again, predicting delivery times, which is real time. You get a predictions request, it comes into a service, you need a predictions response back. You get a delivery in, you process it into a service, you get the value of the delivery time prediction back. So we build this in keeping in line with the microservice architecture into an HTTP service. It's a single service that handles multiple predictors. Main requirement is low latency of the service. And we built it behind a load balancer so we could scale this horizontally as much as possible. In particular, we use Kubernetes containers to deploy the service, and the service is built on Flask. Let's dive into a little more detail on what this prediction service is and what the dependencies are. 3 main ones. There is a model metadata service, a model service, and a feature service. Let's go into the details. Model metadata service is the command center. It keeps track of all models that are live, currently running, that are registered with the prediction service. It gives you can think of having some sort of a JSON interface to it. You have the ID of the model, you have different model status and type and version. Whether it's an experiment model, is it a model that's live in production, what type of a model it is it a regression model or a classification model? The model service is responsible for fetching the model from the repository. So when you get a request for a delivery, let's say you get a request for predicting preparation times or predicting delivery times, model service is responsible for figuring out what the right model is to use. It uses the metadata service to know what the models available are and fetches these models. And since we're going to have multiple requests for the same model, there is a caching layer. And an important part of having these models in production is the ability to test them. So when you have a new model, let's say you come up with a new model for your application, there are 2 ways we test it. One is we do what we call shadowing. When a request comes in, we send it to the shadow model to make a prediction based on it, but not really use it. So that gets recorded, so we can go back and do evaluation on it and look at what the performance is. And the second step, once the shadowing is done, is experimentation, which is mostly we run a lot of A/B experiments. Let's say we have 2 different ways to predict, 2 different models to predict delivery times. we send half the traffic there and half the traffic to the other model and see which one performs better in terms of business metrics. And this model service supports multiple model types. In the previous talk, Mikhail mentioned ensembling and segmentation as different methods, which is you probably are using different models for different markets. The request comes in for, let's say, delivery times. You want to be able to use different models underneath. Or you want to use multiple models and combine the predictions. So the model service abstracts out all the details of it. It handles all the complexity. So it makes it easy to productionize models. Feature service. When you have a predictions request, you know where you're getting the model from. All that's left is figuring out what features to use. Feature service is responsible for talking to the feature store and retrieving these features. If you remember common feature store from the training pipeline, it's extremely important to make sure you use the same features in training and prediction. Using this common feature store helps us achieve this. I'll get into a little more detail on how this is exactly useful when I go into the case study. Similar to how model service supports multiple model types, feature service supports multiple feature types. We could use aggregate features, we could use store embeddings, which are pretty popular, similar to the concept of word-to-vec in natural language processing. The fourth service here is monitoring. When you get a request for prediction, you generate the prediction and you could give it back to the consumer. But also, asynchronously, we send it to the monitoring service to track the predictions. Three particular things we track. Predictions. What's the output coming out of the model? Second is features distribution. What's the distribution of the features that are being used by this model? And the third part is logging. We log all the features and predictions generated for different models. Again, I'll go more into this in the case study. The technologies we use here, we use stats.t server to record all the stats that are used for predictions and features monitoring, and we use segment to log different events. Systems in action. Now that I've described how the system works, I want to take two particular examples of how the system helped us build better ML products. First part, features integrity. Features power most of the supervised models' performance. And it's critical to understand that we have the same set of features, we have consistency of features across different environments, and also we have consistency over time. Consistency across environments means there are no differences in training and prediction time. There are two particular subparts of the system that helps us achieve this. First is the common feature store. Extracting out a lot of the features that are used by the different models we use in production into this common feature store, and using the same features across both training and prediction removes any differences that are possible between the two environments. You're pretty much executing the exact code. It works for most features. There are certain features which might not be able to be powered this way, which is where the second piece comes in, feature logging. When you make a prediction, you have access to all the features you're using and the output of the model. How about you just log it right there, log it in the production system, so that you could retrain on it later. If you do that, you're pretty much training on the same data that your production system is predicting on, so you eliminate more discrepancies between training and prediction time. The only caveat here is it only works for new features. It doesn't work for new features. Let's say you have a model running in production, it's using 100 features, you come up with a new idea. Let's say you come up with a new sort of embedding for representing a merchant. That cannot be integrated into the system because you still don't have access to it in production. It works for all other features. Consistency over time. When you have a system that's predicting and it uses features, there's a good chance things change over time, especially when you depend on multiple data sources. The way we work around this is the features monitoring. The monitoring service establishes metrics to track for different features. For example, you have a feature that's number of items in the order. We track the median values, the mean values, and the P90 values, similar to how you would track an application performance. And doing this, let's say, doing this helps us when there is an issue. Let's say we get paged on predictions not being okay. Having the ability to go look back at the features that are being fed into the system helps us identify areas of discrepancy that we could focus on. The second area that having the system helps us is in launching new models. Previously, once you have the model ready, which is the output of the training stage, someone has to go write the feature extractors on prod, write out the prediction code, which is write out the logic to figure out how to fetch the model, apply the features on the model, have their own rollout logic, run an experiment, run a shadow, and then go on this monitor debug loop. This would take days to weeks. But with the prediction service, once you have the model ready, you could register the model in the metadata service, and the model service figures out how to fetch the model, so you no longer have to write code for it. The feature service has access to different features, so it knows how to fetch those features. And the ability to shadow and experiment means you don't have to worry about the rollout logic. So all you do is you register the model in the service, monitor the metrics, and focus more on building the model. This meant the time to take a model to production reduced significantly. It takes a few minutes to hours to productionize a model now. What are the biggest takeaways? Establishing robust tools are critical to deploying ML in production. Templatizing the ML best practices you identify lets you focus more on the algorithms, which is where all the fun is. Particularly useful tools we identified are the common feature store, the ability to experiment and shadow, and the predictions and features monitoring. If any of these problems are interesting to you, either on the infrastructure side or on the algorithms that I mentioned earlier, hit me up. We're definitely hiring. Those are my details. First name at DoorDash.com, or you can find me on Twitter and LinkedIn. Thank you so much.